Hi all. So today we're going to talk about this problem, 6.25 spring on a T, on page 251. So this problem is basically about this mass on like a T-shaped thing, and there's a spring to it, and the T-shaped thing actually rotates with angular velocity omega. And remember, this is the top view. So basically we can imagine this T to be lying on a table, and so we don't need to consider the effects of gravity. And so that is quite nice. And now the question's asking for r of t. So basically the distance of m from this point here, like we need to get an expression for that. So for this problem, we will utilize Lagrangian mechanics. And so we would need a kinetic energy term. So this motion is actually quite complex because it includes rotational motion, oscillatory motions, and translational motion too. So it's actually quite hard to write out the energy term straight away. So I think we should actually write out the expression for x and y, right? And then afterwards we obtain x dot, y dot, so basically dx dt and dy dt. And then v squared is x dot squared plus y dot squared. And then we can get the energy term, so it's much easier. So let's obtain the expression for x first. So now I will draw a few lines and it should be easier to see. So let's call this angle theta. Well, we form a triangle here. And what is this distance? It should be L cosine theta. And now I'll draw another triangle here. So since this is theta, and this line are parallel, this should be theta too. And then since this is 90 minus theta, so this angle here, right, should be 90 minus theta, and this part's 90 obviously, so this part should be theta. So basically, what is this here? This should be r sine theta. And so also remember that we can always write theta as omega t in this problem, since this thing's rotating at angular velocity omega. So we basically replace all the thetas with omega t. So x is basically L cosine omega t minus r sine omega t, right? And now let's obtain the expression for y. So it's actually quite easy. So what is this part here? This should be L sine omega t. What about this part? Well, r cosine omega t. So basically y is L sine omega t plus r cosine omega t. Now let's get the expression for x dot, which is basically dx over dt, how x changes with respect to time. So let's look at this term first. Is L a constant or a variable? It's obviously a constant, right? Since it's basically the length of the rod here, and it wouldn't change. So we're left with this cosine omega t. And after differentiation with chain rule, we get negative L omega sine omega t. What about this next term? Well, both r and sine omega t are variables, so we should use the chain rule here. So basically, let's differentiate r first. So it's basically r dot, so basically dr dt, r dot sine omega t plus r omega cosine omega t. So again, the chain rule here. And so then let's get y dot, which is dy over dt. So what is dy over dt? Well, it's basically the same thing. So it's L omega cosine omega t for the first term, and then again the chain rule here. So r dot cosine omega t, and then minus, since the derivative of cosine is negative sine, so minus r omega sine omega t, right? And so basically now we've obtained the expressions for x dot and y dot. So now we have obtained the expressions for x dot and y dot. And I actually decided to write this out beforehand, so just in the interest of time and not let the video to be too long and boring. And so remember that in the previous section we had x dot to be negative L omega sine omega t, and basically like this expression here. And now we can rearrange it a bit so it's a bit easier to square it. So let's see, what common do they have? Well, look at this term and this term. They all have omega here, right? So we can actually factor out an omega, and so it's here. So basically we factor out omega, and so we have L sine omega t, and then our cosine omega t corresponding to this, and also this term here, which is here. And then for the y, it's basically the same thing. We factor out omega for these two terms, so basically it's here, and actually we don't forget this term here. And next we can basically square it. So basically let's square the x dot term first. So basically this term here. So first let's call this a and this the b term. So we're trying to do a minus b squared, right? So it's basically a squared minus 2ab plus b squared. So what's a squared? A squared is omega squared, and basically this bracket squared, that's a squared. And then minus 2ab. So basically minus 2ab. So 2a and b. And you times them together and you basically get this expression. And then plus b squared. B squared is here, so it corresponds to here. So that's x dot squared. And basically y dot squared is the same logic. So like we square this term first, and it's here. And then we do 2ab, so this terms times 2, and we get here. And then basically this last term squared again. And now let's actually get the v squared term, which is x dot squared plus y dot squared. And so it's actually quite complex because there are a lot of terms here, but after we combine them together, we can simplify them a lot. So x dot squared plus y dot squared. So obviously it will make sense to first combine the like terms, like this term and this term, this term and this term, and this term and this term, right? Just because you can factor out. So when you combine these two terms, you get basically this expression here. So basically we also expanded this bracket as well. So omega squared and then L squared sine squared omega t, so basically this term squared. And then plus L r sine 2 omega t. So this might be a bit confusing, but actually here, as we see here, so the cross term should be r L r sine omega t cosine omega t. And what do you observe here? Well, we see a 2, we see a sine, we see a cosine. So we should think about the formula sine 2 theta equals to 2 sine theta plus cosine theta. So basically these three terms becomes sine 2 omega t here. And then we have LR. And then we basically have this squared again. So we basically have this squared. So here and here. And then basically we continue to expand. And then also for this r dot squared term, this plus this, well, sine squared plus cosine squared is 1, right? So it should be r dot squared here. And then we combine these two terms, and we basically get an expression like this. And again, in the interest of time, I'm just not going to write it out completely. So feel free to try expanding it one by one in your own time. And so then after we obtain the expression for v squared, we basically can find the Lagrangian, which is k minus u. So basically, k is half mv squared. So m omega squared L squared plus r dot squared plus 2 omega L r dot minus u. So let's go back to the very top. So what potential energy do we have here? Well, since this is a top view and it's on the table, there's no gravitational potential energy. And so there's really only the spring potential energy. And the expression for that is half kx squared, or r squared in this case. So it's basically minus half kx squared, kr squared. And now we're trying to obtain a function of r of t. So we have this formula, the Euler-Lagrangian equation. So basically, let's do this. So d dt, so what is here? What is this? Well, how many r dot terms do we have? We only have this and this. So all the rest becomes 0 because they basically are constants when you're differentiating with respect to r dot. So what we get here is m r dot plus basically this m omega l term. And then equals to partial L over partial R. So we have this term here and this term here. And these two terms we can ignore. So basically this becomes this, so we're doing dr so then the left side becomes mr2 dot, and then since this term is a constant, it's basically 0. Now about here, well, we utilize the chain rule again. So what let u be L squared plus R squared? What is du dr? Well, it should be 2r, right? So then this differentiation basically is r m omega squared r, and then basically L squared plus R squared. Oh, sorry, it should be, so this term disappears. So basically, it should be m omega squared R. And then what about this term? It just becomes kr. And so we have now obtained the expression for, we have now obtained a differential equation. And so let's rearrange this a bit. So let's divide by m first. Does this look familiar now? So like, let's continue to rearrange it, factor out the r. This should look very familiar now. And now, based on the formula here that we derived, we can basically see that the special value for omega, let's call it omega star, is k over m. And now let's talk about the behavior of the mass above, equal, and below that threshold. So, when omega is smaller than k over m, we basically get a sort of oscillatory motion, and the spring force wins over the centrifugal force. So r of t should be the form of a cosine capital omega t plus phi. And so phi, where phi is k over m minus omega squared. And then next we have the case when omega is equal to k over m. And then the motion will be r of t equals to c1 plus c2t. And this is when the system is sort of in an equilibrium, and the mass will stay where it is or drift along the rod at constant speed depending on the initial velocity. And then for the third scenario, when omega is larger than k over m, basically the centrifugal force wins over the spring force. And so this is sort of like an exponential motion. So the function, the r of t should be the form of, let's call it C3, e alpha t plus C4 e minus a negative omega t, where alpha is equal to omega squared plus minus k over m. And so this is basically when the centrifugal force wins over the spring force, and the mass will continue move and accelerate outward along the rod radially. And it will eventually fly off the rod, basically.